Okay, so this is about L'Hopital's rule. That's how you say this. Um, L'Hopital's rule is a theorem that's going to help us find limits that we maybe would have had a tough time finding before. Um, Here it is. There's a technical condition about how these have to be differentiable functions on an open interval I, but we're not going to have to worry about this too much. I'm only going to ask you questions where involving functions that are differentiable. Um, Now, what L'Hopital's rule is, it's about a limit of f of x over g of x, and it's about doing this in cases where it's not so easy. For example, if in the first star they're both going to 0, so f of x is going to 0 and g of x is going to 0 as x goes to a. And we dealt with a lot of limits like that, and we found that, that there's a lot of tricks we figured out to dealing with limits if you're getting 0 over 0, but those are not so easy. Similarly, if this is going to infinity and this is going to infinity, or negative infinity, if the top and bottom are going to infinity or negative infinity, or maybe the top is going to positive infinity and the bottom is going to negative infinity, this is also not so easy. But L'Hopital's rule tells you that this limit is the same as this limit, where on the top now I have f prime instead of f, and on the bottom I have g prime instead of g. Assuming that this limit actually exists, they're equal. So let's apply L'Hopital's rule, and let me just point out before we even do this that this is a limit that we know how to do already. We could do the conjugate to this. This is 0 over 0, because if I plug in 4 for x, I get 0 on the top and 0 on the bottom. So we definitely have to do something, but I'm just pointing out that we knew how to do this in like the first week of class when we were first doing limits. We would do the conjugate, but I'm not going to do the conjugate this time. I'm going to do L'Hopital's rule. Now, whenever I use L'Hopital's rule, I want to justify that I can use it at least in one little way. This limit is a 0 over 0 limit, because if I put in 4 on the top, I get 0, and on the bottom, I get 0. So I call this a 0 over 0 indeterminate form. That's justification that I can use L'Hopital's rule, because that's like this first scenario, where the top is going to 0 and the bottom is going to 0. So I'm going to write something there that this is just to justify that I can use L'Hopital's rule. And now I'm going to go ahead and use it. So they do the derivative of the top. So this is x to the 1/2, so I can do 1/2 x to the minus 1/2, and then the 2 will just go away when I do the derivative of the top. And the derivative of the bottom is just 1. And now I look at this, I try to plug in x equals 4, and now I find that I'm not dividing by 0 or anything. I can just do it. 1/2 4 to the negative 1/2. 4 to the negative 1/2, that would be 1 over 4 to the 1/2, right? 4 to the 1/2 is 2, so this is, there we go. Okay. Let's do this one. This is another one that we already know how to do. As x goes to 3, if I try to plug in 3 in the top, I'm going to get 0. If I plug in 3 in the bottom, I'm also going to get 0. This is a 0 over 0 indeterminate form, just like the last one. We already have the tools to know how to do this. As you can imagine, you can factor the top into x plus 3, x minus 3, and you can factor the bottom into x plus 4, x minus 3, and then cancel the x minus 3's and plug it in. These are skills that we've already had. I'm not going to do it that way. I'm going to do it using L'Hopital's rule this time. First, let me justify that I can use L'Hopital's rule. And we already talked a little bit about that justification. The justification is because if I put in 3 for x, I get 0 on the top and 0 on the bottom. So that's, I call this a 0 over 0 indeterminate form, and that's my justification that I can use L'Hopital's rule. So this becomes, derivative of the top is just 2x, derivative of the bottom is 2x plus 1. And now I ask myself, can I just plug in 3 for x? And I find that I can. I get 6/7. Yeah. Okay, let's do another one. This one, maybe we wouldn't know how to do before this section, but now we're going to be able to do this. As x goes to pi, okay, we have to actually think now. Cosine of pi is -1. So if I'm putting in pi on the top, I'm going to get 0 because it's -1 plus 1. Sine of pi, meanwhile, is 0. So actually, this is another 0 over 0 indeterminate form, meaning I'm going to use L'Hopital's rule. Derivative of the top is negative sine x. Derivative of the bottom is cosine x. And now I ask myself, can I plug in pi for x? And it looks like I can, because sine of pi is 0, cosine of pi is -1. So I wasn't getting 0 over 0 anymore. I was getting 0 over -1, which is fine. That's just 0. Okay. Right. Now, so I've done 3 examples so far, and they were all 0 over 0. There are other indeterminate forms. For example, there's infinity over infinity, and that was kind of the other case that we're allowed to use L'Hopital's rule on. And then there's these others, and these are just forms of limits that are difficult to find, but we can typically find them using L'Hopital's rule. We're about to see 0 times infinity. Because, whoops, actually, let me make sure this is the limit as x goes to 0 from the right. Well, as x goes to 0, this is going to 0, and what happens to natural log of x? Well, here's a little tiny graph of y equals ln x. It has a vertical asymptote at x equals 0. As x goes to 0 from the right, this goes to negative infinity because it's going down, down, down to its vertical asymptote. So, once again, as x goes to 0, this part's going to 0, this part's going to negative infinity. When we're talking about L'Hopital's rule, we don't distinguish too much between infinity and negative infinity, so I would call this a 0 times infinity form. Maybe more specifically, it's like a 0 times negative infinity form, but we don't have to distinguish between the names of 0 times infinity and 0 times negative infinity for this. So what do we do? This is an indeterminate form where we have to use an algebra trick first, and then we can apply L'Hopital's rule. So I am not using L'Hopital's rule just yet. What I'm going to do is a little algebra trick. Multiplying by x is the same as dividing by the reciprocal of x, right? That's the same thing. And why would I write it this way? Now, this limit is something that I can use L'Hopital's rule on, because this. The top, as we discussed, is going to negative infinity. The bottom, 1 over x, as x goes to 0 from the right, 1 over x goes to infinity, right? I can draw a little graph of 1 over x here. Yeah. And this also has a vertical asymptote at x equals 0. So, right, so this is an infinity over infinity indeterminate form. And that is something that we can use L'Hopital's rule on. That's like this. So I write the same limit. I'm going to do the derivative of the top. The derivative of natural log x is 1 over x. The bottom, okay, the bottom is like x to the minus 1, so its derivative is negative 1, x to the minus 2. Like that. Okay. Now let me clean this up just a little. So this negative 1, that's just going to give me a negative sign in front of everything. This is 1 over x times, I have a negative power in the bottom, so I can turn that into multiplying by x squared. And then I would cancel an x. And now after cleaning it up, I realize now I can just plug in x equals 0. Yeah, so we're good. Okay. So there are still more indeterminate forms. So take a look at this one. The limit as x goes to infinity, 1 plus 2 over x to the 3x. So if you look at what's in parentheses, this 2 over x is, of course, going to 0 as x goes to infinity. So in parentheses, it's basically 1. So what's in parentheses is going to 1. The power is going to infinity. So I would call this 1 to the infinity form. And that is on our list. There's these 3 forms, 0 to the 0, 1 to the infinity, infinity to the 0, and we do something similar to all of these, that they involve exponents. Right, so here's what we do. Let me call this limit L. So what I'm going to do, I'm going to find the natural log of L. So I'm taking the natural log of both sides, and natural log is a continuous function, meaning I could write the natural log and then parentheses around this whole limit, or I could do this. I can put the natural log inside the limit. And why am I doing this? Well, I'm going to use log rules to take this down. So we're here. Now let me take a look at this again. As x goes to infinity, this part goes to infinity, obviously. This part, well, this thing in parentheses is going to 1, and what natural log of 1 is 0. So, in conclusion, this is going to infinity, this is going to 0. So I have an infinity times 0 form now. Well, what do we do when we have an infinity times 0 form? We had one last time, and we did this algebra trick where you create a fraction out of this. So let's try that again. Now this 3, yeah, I don't want to think too hard about this 3. 3 is just a constant. I can pull that all the way outside of the limit. Other than that, I'm going to take this x, and instead of multiplying by x, I'm going to divide by the reciprocal of x, which is x to the minus 1. And now, what happens here? As x goes to infinity, okay, the top is natural log of 1, which is 0, so the top's going to 0. The bottom's also going to 0. As x goes to infinity, x to the minus 1, which is 1 over x, that goes to 0. So this is a 0 over 0 form, meaning I can now apply L'Hopital's rule. Okay, what's the derivative of the top? I'm using the chain rule, so it would be 1 over 1 plus 2 over x times the derivative of the inside. This is 2x to the minus 1, so I can write 2 negative 1 x to the minus 2 for the derivative of the inside. And then I do the derivative of the bottom, which is negative 1 x to the negative 2, right? And then I see I can cancel this and this, right? And now let me look at this again. As x goes to infinity, this 2 over x goes to 0, and I think I'm good. I can just write everything down. So this is 3 times, okay, as x goes to infinity, this whole thing looks like it's just 1 over 1 times this 2, and then everything else canceled. So I get 6. Now when you do this, there's one last thing you have to remember. The original limit was L, and actually what we found was natural log L. That was the first thing we did, is we did natural log of both sides. So L is not 6, the natural log of L is 6. We still have to find L, but this last step is easy. The way you would get rid of this natural log is you would do e to both sides. So L is e to the 6th. So that's the original limit. Okay, what else? Okay, how about this one? This, since x is going to infinity, the base of this is going to infinity and the power is going to 0. So this is an infinity to the 0 form, which is, that was another one that was on our list. But I told you, these 3 involving exponents, we're going to treat them all the same. We're going to do the natural log trick that we just did. So I'm going to call this L. And then what's the natural log of L? I just put a natural log inside the limit. And now I can use natural log rules. I can take the power down. Right? It's out of focus. There we go. Let me write this just as a fraction, natural log x over x. And now as x goes to infinity, the top goes to infinity and the bottom goes to infinity, right? We should know this. As x goes to infinity, the natural log of x does go to infinity. So this is now an infinity over infinity form. So I can use L'Hopital's rule directly. The derivative of the top is 1 over x. The derivative of the bottom is just 1. And now as x goes to infinity, this just goes to 0. And for the last step, we just have to remember the same thing. We didn't find the original limit. We found the natural log of that limit. So I have to find L, but that, you know, L is just e to the 0 then, which is 1. Okay, good. The last indeterminate form that I'm going to talk about is infinity minus infinity. It's like asking what happens if I take a huge number and I subtract another huge number. It depends. How do you compare the hugeness of these two numbers? If the first number is much bigger than what I'm subtracting, then I can subtract it and there will still be a lot left. But if it compares the other way, then who knows? It's hard to predict what happens if you take a huge number and you subtract another huge number. You really have to know about the relative size of the two numbers that we're talking about. Anyway, that's like that. Here's an example of that. As x goes to 1 from the right, remember that natural log of 1 is 0. So this is like 1 over 0, which is like infinity, right? This is also like 1 over 0, which is like infinity. So what we have is an infinity minus infinity form. Right? This can be the hardest to deal with, but one idea is if you have fractions, just get a common denominator. So I guess I would be multiplying by x minus 1 over x minus 1 here. Actually, I won't be lazy. Here, I'm really showing my work to get the common denominator, right? X minus 1 minus ln x over x minus 1 times ln x. Yeah, okay. Now as x goes to 1, what happens? Here I've got 0 minus 0, so the top's going to 0. On the bottom, it looks like I'm getting 0 times 0. So this would seem to be a 0 over 0 form. Okay, good. That's one of the ones L'Hopital's rule applies directly to. So I do the derivative of the top. That would be 1 minus 0. This goes away. Minus 1 over x. And then what do I get on the bottom? Well, I have to use the product rule. So derivative of this is 1 times ln x plus x minus 1 times the derivative of ln x, which is 1 over x. Okay. I guess let's check something real quick. I'm checking, can I just plug in x equals 1? On the top, I would get 0. On the bottom, I would get, keep in mind, natural log of 1 is 0, so I would get 0 plus, and this would also be 0, because this part is 0. So if it looks like if I try to plug in x equals 1, I get 0 on the top and 0 on the bottom still. So I still have some work to do. Maybe let me try to clean this up. One thing I don't like about it is I have fractions inside of fractions. So maybe let me multiply the top and bottom by x just to kill the denominator here. So this is going to give me x minus 1 on the top, and on the bottom it's going to give me x ln x plus x minus 1, like that. Okay, and I can try this again. If I try to plug in x equals 1, you know, I'm just hoping for a miracle and hoping that something changed. But if I plug in x equals 1, I still get 0 on the top, and on the bottom I get 0 plus 1 minus 1, which would be 0. So this is still a 0 over 0 form. So this is good. What we often do is we just use L'Hopital's rule again. I have a 0 over 0 form. Why don't I just use L'Hopital's rule again? So the derivative of the top is just 1. The derivative of the bottom, let's see. Here I have to use the product rule, so I'm going to have 1 times natural log x plus x times 1 over x, because that's the product rule from this, plus 1 minus 0. Yeah? Now, at this point, you might be afraid that we're just going to go forever, but have some faith here. If I plug in x equals 1 now, on the top, I definitely don't get 0. On the bottom, okay, here I get 0, so I'm starting to worry, but here I get 1, and here I get 1. So it looks like if I plug in 1 now, I get this, which is 1/2. So yeah, one moral of that story is don't be afraid to use L'Hopital's rule multiple times. You might use L'Hopital's rule once, and that changes the derivative to something else, but then you try to work with that and you realize that it's still 0 over 0. You can use L'Hopital's rule again, and sometimes you actually end up using L'Hopital's rule several times. I'm not gonna, you know, I'm not a mean guy, so I'm not gonna give you a problem where you have to use it 10 times or anything like that. But there are problems where you have to use it 10 times. So I'll keep it down to maybe 2 or 3 times that you have to use L'Hopital's rule. But don't be the point is don't be afraid to use it more than once.